Hello.
Yeah, hello. Yeah, can you hear me?
Yes, sir. Good evening, sir. I have regarding one doubt, sir.
Okay, yeah, tell me.
I'm doing to PhD research on earthquake resistant design using optimization method, sir.
Okay.
Regarding that, I have some a small doubt, sir. I am calling to personally, sir. If you have any problem.
Okay, you can call me after the class.
Okay, sir. Is there any phone number or mail ID?
Yeah, you can note down. I will give my mail ID. Okay.
Okay, sir. Through mail, I have to reply, sir.
Yeah, yeah, yeah. I will. You can send there. I will reply there.
Okay,
I am
sir.
writing the mail ID in the chat.
Okay, okay, sir.
Okay, you can mail me here. Yeah, I can. I will reply. Okay, whatever doubts you have.
Okay, okay, sir. Thank you, sir.
Okay. Okay, then I
Sir,
think. Yeah.
sir, in this course, is there artificial neural network is covered, sir?
No, no, no. You
Inversion.
know, in this course it is not covered.
Okay,
ANN, for that you will have to like take machine learning kind of course. So
okay, okay,
okay, yeah, this is I think the optimization is the basic for like doing machine learning. That there are two things. One is statistics. You should know statistics properly,
okay,
correlation and this kind of things. And after that is optimization. If you know these two things properly, then you can do machine learning or artificial neural network and these kind of things. Okay.
okay.
Okay. Okay, then yeah, we'll get started for today. I think it's 3 minutes past 7. Can you see my PPT?
Yes, sir.
Okay. Yeah. Welcome to week 10 of this problem solving session for this course optimization methods for civil engineering. So this is Diljit Datta from IISc. So today in this uh, session we will be covering like basics of this particle swarm optimization, and then we'll also see through what is evolutionary statistics. So these are taught in class. I will just go through the basics and we will solve the code. And if there are any doubts in the code, you can ask me. Okay. Okay. So first, coming to evolutionary statistics, it is similar to genetic algorithm but slightly different. One thing is it in genetic algorithm we had like both real coded genetic algorithm and also binary coded genetic algorithm. But in this evolutionary statistics, we'll only have this real parameter value. We won't have any binary values. Secondly, ES does not use crossover operator. Crossover is not taking place here. We'll only do selection and mutation. It is just like real coded GA with selection and mutation operators only. So this ES algorithm, it can be like two-member ES or it can be a multi-member ES. So based on our like based on our problem statement or the type of problem we are facing, we will be either using this two-member ES or multi-member ES based on our requirement. First, let us see through what are the steps to solve a problem using the two-member ES. In two-member ES, what we do? First, we choose the initial solution X and then a mutation strength sigma. So the mutation strength sigma, it depends on a Gaussian distribution. So you can see, so we create a mutated solution by taking a value from X which is at distance sigma. At a distance sigma from the solution. Now that distance sigma is no, like one second. Okay, okay. Okay. So this not distance sigma. The thing is that we'll get a value from a normal distribution from by using this 0 comma sigma. So n 0 comma sigma, you can know it is a bell curve with mean 0 and the standard deviation sigma. If we have this normal distribution curve, from that we can get a point in that curve randomly by generating from our computer code. And then what we do, we add that value to the value of x, that is the initial solution, and we get a value y. Now we'll do the function evaluation for y and function evaluation for x. If the value of fy is less than fx, we'll replace x with y. So one like major difference between es and ga is that in ga we always try to maximize the solution, but in es we'll try to minimize the solution. So it is good for minimization problem. So if we have a maximization problem, we'll convert it to a minimization problem by multiplying the this one fitness function by a minus sign. So after termination, so in this way we'll proceed from it for each step. Like we get a solution y, and from that we will see if the next solution is better than that solution. So if termination criteria is satisfied, then we can stop. Termination criteria is based on number of generations, or the now like we give a tolerance level. Based on tolerance level, we get a termination criteria. So in this two-member ES, the strength of the algorithm is the proper value of sigma. So if we take a higher value of sigma, then what? There will be higher diversity in the value. So the mutated value will be far away from the initial value. So in and if we have a very small value of sigma, then the mutated value will be very near to the the initial solution. So depending on that, we have to select our solution. Sometimes the thing is that our solution space is not that diverse, and we are like the initial solution is somewhere near the global maximum minima only. So in that case, if we take a mutated solution that is far away from the initial solution, we won't be getting the global minima very fast, like very easily. So we'll have to do a lot of iterations. So that is why if we, for in that kind of case, we have to take a sigma value that is very small, so that our the mutated solution is generated somewhere near the initial solution. And second is the Richenberg postulate. This is a postulate stated by Richenberg. He told that the ratio of successful mutations to all the mutations should be equal to 1 by 5. If this ratio is greater than 1 by 5, then increase the mutation strength. If it is less than 1 by 5, then decrease the mutation strength. Now, how do we increase and decrease the mutation strength? We can increase and decrease it by changing the value of sigma. If sigma is high, our mutation strength will be high. If sigma is small, our mutation strength will be small. So this was about two-member ES. Now, similarly, we can have a multi-member ES. In multi-member ES, what we do? We choose the initial population of mu solutions and a mutation strength sigma. So we create lambda mutated solutions. So like for each for each of these mu solutions, we can have a lambda, that is lambda number of mutated solutions, and you can generate in this order: yi is equal to xi plus n 0 comma sigma. So combine mu and sigma and choose the best solutions mu, and then terminate. Else go to step 2. So we'll see. Okay, I think someone is trying to join. Okay, so we'll see a code for one multi-member ES and also for a two-member ES. So after seeing the code, it will be more clearer. So this was about evolutionary strategies. This is a very like efficient method when you want to do a minimization kind of problem. Now there is this particle swarm algorithm. So this algorithm is based on this method of flock of birds. So what happens, like when a flock of bird is like flying or in the sky, suppose they see a piece of food or piece of something prey. So what they will do, they suppose the one bird that is in the first, like in the first row, so that bird will spot the food first, so it will change the direction, change its velocity towards the food. So what the other birds will do, other birds will also try to follow that bird so that they get near the food. So this is the like basic uh, so basic concept behind particle swarm algorithm. So this concept can be applied in our optimization method also. So what we do, each solution is considered as a bird called particle. Now all the particles have a fitness value. The fitness value can be calculated using an objective function. We have an objective function. So based on the objective function, we can have a fitness value. Now all the particles preserve their individual best performance, that is they have the memory. This is the one major advantage of particle swarm algorithm, that all the particles preserve their have their memory of the best performance. So the thing is that they all the, suppose in the flock of birds also, like all the birds will be moving towards the target, but at some point the bird, one of each bird will be some near to the target, so they will remember that position, that is like when they were near to the target. So a similar method will be applied in while we're doing the algorithm for our problem, that is they will preserve the best performance even after doing a lot of iterations. And they also know the best performance of their group, they can communicate with each other. That is, the if one of the solution, one of the bird has attained the nearest, that is nearest to the target, that information will be passed to the other birds also. So similar is method we'll be using here also. And then they adjust their velocity considering their best performance and also considering the best performance of the best particle. So this is the method. So in the right side you can see the flow chart. So what are the steps? One thing is initialize the particles, then evaluate fitness of each particle, then we have to modify the velocities based on the previous best and the global best position, and then we set a termination criteria based on a number of steps, or we can set it based on a tolerance level, that is how far near it is to the target, and lastly we can stop the iteration. So in every iteration the velocity is updated. So how do we update the velocity? It is updated in this formula, that is vi equal to omega vi, vi plus 1 equal to omega vi plus c1 into we generate a random function, and pbi minus xi plus c2 into generate random number into gbi minus xi. I won't be going too much details into how this is formed, because this has a lot of uh, concept behind it. So thing is that we need to apply the just apply the concept for our problem. So we just need to understand what is the basic thing that is going inside. So the first term is called the inertia term, that is the initially what is the velocity, and based on that how it will change its position and change its velocity for attaining the next best solution. So what we'll do to get the next best solution, first it will do a local search, that is near that area, what is near the area it will do a local search based on the initial solution, and then it will see if there is a good solution in that area. And third term it will do a third term, what it does, it does a global search, that is it searches throughout the search space, and it will see if that particle is attaining a global maxima or global minima. So what we do in this method, like both local search and global search are done simultaneously, and after obtaining this global doing this global search and local search, we will update the position based on xi plus 1 equal to xi plus vi. It is based on that updated velocity. Now here c1 and c2 are the learning factor, and omega is the inertia weight. So you can see this in this plot, like initially we have xi, it has this direction vi. So how do we get the next position? So next position we get by getting, suppose we have this pbi, this personal best performance, and then we have the best performance of the group. So gbi, that global search, is done based on the performance of the whole group of the solutions, and pbi is done only on the personal basis, only of that particle what it attained in that step. So it will update the vi based on these two values, and finally we can get xi I plus 1 by adding vi plus 1 to xi. So this is a steps for PSO. So we create an initial population of agents uniformly distributed over search domain. So it generate suppose 20 or 50 sometimes that kind of solutions randomly in the search domain. Then we evaluate the, see in this case we don't start with only one solution, we start with multiple solutions so that we have in the we're following this flock of birds. So in flock of birds there are like lot of birds that is trying to get the optima. So we'll have a lot of initial solutions and all the solutions will be trying to reach the optima. So evaluate position of each of the particles according to the objective function. We do that using the fitness function. Then if the current position of a particle is better than its previous best position, then update its personal best position. And then in the group we find the best particle of the population. So after each step we get a personal best for each of the solution, and among the personal best we find one best solution that is called the global best solution. So we'll update it after each step. So the number of particles initially we consider like between 10 to 50. Now C1 represents the importance of personal base, C2 represents the importance of neighborhood base value, that is from the global base. C1 plus C2 generally considered around 4. So these are empirical values that has been given like after people have done a lot of experiments. When the velocity is too low, the algorithm is slow, and the velocity is too high, the algorithm becomes unstable. You have to remember, because if the velocity shouldn't be too slow or it shouldn't be too high. And the thing is, the one thing is there is no selection procedure in PSO. The thing is here, all the solutions will be trying to attain a best solution. And PSO is the only evolutionary algorithm that does not remove candidate population members. And yeah, since there is no selection, and also PSO combines local search methods with global search method, attempting to balance exploration and exploitation. So simple, easy to implement, and computationally efficient. The thing is that you have to select the initial population carefully. So it shouldn't be like you are selecting too many samples or selecting too less samples. So based on the problem or based on the search space, you have to select the appropriate number of solutions, and that you can get by like trial and error only. You're repeating the code after for different initial population, and you'll see for which number of initial population you're getting to the optima efficient, like quickly. Okay, there are some small questions. So after this we'll proceed to the code. So which of the following statements is not correct about evolutionary strategies? So ES uses real parameter values. Yes, this is true. ES uses crossover operator. No, it doesn't use crossover operator. It is just like real coded GA with selection and mutation operators only. Yes. Yeah. So 1 and 3 are true, and the second option is false. In its second question, now in its iteration, one parent creates one offspring by using the Gaussian mutation operator in two-member ES. Yes, that is true. In ES, what we do is do a Gaussian mutation, that is use yes, n0 comma sigma, and
With screen not showing, sir. You are explaining of I can't see that screen. Yeah, yeah. Thank you.
okay. Now you can see, right?
Yes, sir. Yes, sir.
Okay. In each iteration, one parent creates one offspring by using the Gaussian mutation operator in two-member ES. Yeah, that is true. We get the next solution after we get the next solution from the parent solution by using a this is xi plus n0 comma sigma. So this is the method y equal to x plus n0 comma sigma. Third question, which of the following statements is correct about Reichenberg postulate used in two-member ES? The ratio of successful mutations to all mutations should be equal to 1 by 5. Yeah, that is true. The ratio of successful mutations to all the mutations is greater than 1 by 5. We have to increase the mutation strength. Yeah, that is also true. And statement 3, if the ratio of successful mutations to all the mutations is less than 1 by 5, we have to decrease the mutation strength. Yeah, that is also true. All our three statements are true. Now, during optimization, particles from optimization carries out both local and global search simultaneously. I have already discussed now. So it is option number C. Now, uh, in comparison with a genetic algorithm, particle search optimization is expected to be more efficient and computationally faster because it is doing this local search and global search simultaneously. So it is more efficient than GA. And suppose the population size is n and the number of iterations is t. Population size is n, the number of iterations is t. How many times will the objective function be evaluated, including the initial objective function evaluations in particle swarm optimization? So initially there are n is the population size. So for each of the initial population, for each of this particle, we will have to evaluate the evaluate this objective function, that is fitness value. So n we have to add. Now for to this n, what we have to add? We have to add a number of iterations. So now for each iterations, we are calculating this objective function n times because each of the n samples in the population are used for evaluating the fitness function in each of the iteration. So in including the initial iterations, what will be the total number of iterations? Total number of function evaluations, it will be n plus n into t. Okay. So these are some basic questions. So there are two coding questions. Before that, I will proceed to the code part. Okay. Okay. Can you see the R screen?
Yes, sir.
Okay. Yeah. So initially, what we do, we will do one or two problems using this evolutionary strategies algorithm, and then we'll do two problems using this particle swarm optimization. So this question is first being solved for ES algorithm. Okay. So we will take this function, that same function we're trying to solve using GA also. So a similar function we'll be taking for here also. So and yeah, remember in ES algorithm we did not load any library because there is no specific function directly for doing this ES algorithm. We will simply use a while loop, and so this while loop and for loop and these are there in this base R only. So we need not load any library. For particle swarm optimization, we have to load the library PSO. So remember that. So yeah, I will clear the workspace for now and we'll see. Okay, so we have this function. So yeah, let us see. I will run this function. This we have the function. Now we'll do the function evaluations where both x1 and x2 are varying between -5 to +5, and we are generating in a sequence of 0.1. So we got x1 and x2. So there are 101 values in both x1 and x2. Now we do the function evaluation for each for this x1 and x2 by using this outer function like we discussed in last class. So we get the function value of z. Now we have to plot this z and we will see the contour plot of this z for these levels, that is 400, 300, 200 and up to 0.1. Yeah, so I think the plot is, yeah, can you see the plot? Yeah, this is the plot for the function. So you can see there are 4 places where there is a minima, I think. Yeah, so there is a minima. So there are 4 places where there is a minima, and we have to see and to search, do a global search for all this for all this global maxima, and sorry, global minima among all this minima. So what we'll do, we'll use the evolutionary strategy algorithm. So if you remember, when we solved the same problem in GA, we multiplied it by a negative sign because you have to find the minimum. But we are not multiplying with the negative sign here because in ES algorithm, it is designed to get the minima only. So we will do the function evaluation directly without multiplying by the negative sign. Just remember that. So these are the contour levels. So there's 400, 300, 200 till 0.1 we have done for each of the for this around 10, 12 levels. Yeah. So for ES algorithm, what we have to do? First we have to define sigma. So we take a sigma value of 1. Okay. Take a sigma value of 1. We take generation equal to 100 because we will be doing around 100 iterations. We take 100 iterations. Then we take number of variables. Number of variables will be 2, x1 and x2. So we take n var equals to 2. Then initial population size, we discussed that initial population size should be in the range of 10 to 50. So we take around 20 solutions and we'll proceed with those 20 solutions. Do we take population size? Then the lower bound is c minus 5 comma minus 5. Yeah, upper bound is c 5 comma 5. Okay. Now we have to generate a initial population. Now initial population, it should be size of 20. So how do we generate? So we have to generate 20 solutions like for both x1 and x2 because x1 and x2 are points like x and y coordinates of a point. So we have to get 20 values for each of x1 and each of x2. So how do we do it? Do that. So for x1 we run this command. It is run if population size minimum is equal to lower bound 1 and maximum equal to upper bound 1. Lower bound 1 will give this first coordinate, upper bound 1 will also give this first coordinate. So in this range we generate 20 samples. The population size is 20 random samples, and to generate these random samples, this is the function that is used, run if. Okay. Similarly, we generate a population for the second that is x2 again in the same range. So we run this command. We got the initial population. We got this initial population. It has 40 values. 40 because we have done both x1 and x2. So we write this for and 40 is in the terms of 1D array. So we'll try to convert it to a 2D array so that it represents in a form of point. So now you can see, yeah, inipop is a 20 by 2 array. So we'll just have a look at inipop initial population. So you can see, so there are 20 points and each point has one x coordinate and one y coordinate, is x1 and x2. So and these are values are in the range of -5 to 5 for both x1 and x2. Now let us see what is our initial population. So I'll color this by green. Okay, let us see. So initial population we have. So we'll just see the plot how the initial population generated in the sample space. We can see our like sample space. It shows that all the initial population generated randomly in the sample space, and it is spread all over the space. It's not like it's concentrated only one region of the sample space. You can see there are some values in the left, some in the right, some in the center. So our initial population is will diversified in the sample solution space. Now let us do the function evaluation for this initial population. How do we do that? We do that using this f function. F of x1 comma x2 is there. So we get initial function value for the initial population. We got the function value, so we now get the update the initial population array by adding this function values to the right. So you would use this cbind function. So we got the initial population. Now you can see initial population has how many columns? 3 columns. The first column is x1, second is x2, and third is f0. F0 is the value of the function at x1 and x2. 1 second, okay, just a second. So yeah, we got an initial population. Now we'll do the fundamental steps for the ES algorithm. So we generate index I, the initial value is set to 1. Now we will use a while loop. I think the format of while loop have been taught in class also, and I also taught in last class. So while I is less than generation, we took generation is size as 100. So when I is less than gen, so how do we do that? So initially what we do, we generate a new population which takes only the first 2 columns of the initial population. And to get the first 2 columns, what command is there is initial population square bracket. Comma means like if you're putting comma and not putting anything here, it means it is taking all the rows. And -3 means was if it is removing the third column. Okay, so it is removing the third column and you're taking on the first 2 columns and all the rows. So it is all the x1 and x2 values. Now, yeah, and this is the ES algorithm, that is multi-member ES. Okay. Now we have to do the mutation. How do we do the mutation? It's like we first generate uh, 40 samples using this rnorm function. Rnorm means rnorm function is used to generate random values from the normal distribution with mu and sigma. Here mu is 0, that is mean is 0, and sigma is the standard deviation, and SD we took as how much? We took as 1 and 0, 1. So I write the command generate okay. So using this rnorm function, we generated around 40 samples. For these 40 samples, we'll arrange that in a this for 20 by 2 array, because we have to add those values corresponding to each x1 and x2 value. So we arrange that in an array form. In this mutation, dimension is given as C of population size comma n var. Population size is 20 and n variable is 2. So it will dimension take an array of into 20 by 2. Now we update the new population by the formula. This new population is new population plus mutation, that is why we're getting yi. So after getting the yi values, we have to do the function evaluation for this new population. We do it using this f new population 1, new population 2, that is f of x1 y1 comma y2. We get the function values. Now what we do, we'll do the column bind of new population and f naught. That is, I showed here in initial population what we do, use the c bind function to place the function value for x1 x2 in the right side. So we got this. Now after that, we got a new population of 20 values. So we'll put that together with the old population. And how do we do that? We do it using the rbind function, and we can see it this new population is placed below the initial population, and this is done using the rbind function. So Now we got all the population. This initial from the first solution and from the second set of solution, that is after mutation. Now what we have to do, we have to arrange these all these solutions in the form in ascending order, that is ascending order of their function values, because we are looking for a minima. What happens in there are some suppose in selecting the first population, there will be some samples or some x1 x2 values where we have already near the minima, so we have to preserve that for our next solution, right? So how do we do that? We convert this all population array to a data frame, and this data frame is now arranged in the form of in the ascending order. To arrange in the form of ascending order, we have to use this order function based on all population hashtag dollar f naught. Okay, so we arrange this in ascending order, and from this after getting arranging all the solutions in ascending order, we will take the to a top 20 values, because our population size shouldn't change. We are proceeding to the next generation, so we'll take only 20 values from this and top 20 values, and we will proceed to the next. So there now this top 20 values will be the initial population for the next solution, that is the next generation. So we can proceed it to the 100th generation, and we will see the contour plot for each of these after each iteration, and again the same contour function is used, and the system.sleeve is 0.1 to see the visualize the solution. Okay, so we'll run this while loop, and we'll see how the solutions are varying. Just take a view, take a glance on the graph on the right side, how the green dots are varying. I think, okay, 1 second. It's not Z, I have to use it is capital Z, sorry. Now see in the right side how it's for each generation the samples are being, initially it was spread all over the space, now it is getting towards the global minima, that is near the top right minima. So after some number of iterations, all the solutions will be aggregated near the local, that is global minima, and among that we will have the best minima. Okay, I think it is still running. Yeah, so we got the solution. Now we'll see what is the x1 x2 value. X1 x2 is 2.99 and 1.99, resistance 3,2, and the best solution that of f function value is 0.002, that is near 0 only. You won't get the exact solution because it is a this method is done using this meta heuristic part. So if we use deepest descent then together, then we can get a exact solution. Okay, so this was the multi-member ES. Now we'll see the similar problem using the two-member ES. So again here what we do, here we put that sigma value, that is 1. Generation we put 1000. Let us keep it high, since we have only two members, we don't have multi-members. So number of variables is 2. Okay, initially we take the x naught, the initial population as c 2,2. That is only uh, X naught will take as C2 comma, there's only one solution in the beginning. And yeah, we'll run X naught is and we'll write. Okay, I think we put it as purple color to visualize this properly. We can see that the initial point, 1 point is generated here. So now we'll run the two-member ES code. So how do we run that? So first, initially we generate this I index, take it as 1 now. While I is less than generation, that is, we have to generate for 1,000 generations, and for each generation, we have to do the function evaluation. And we're taking higher number of generations because we are taking only one's initial population, that is one sample, 1 point only. And for doing it 1 point, if we take less number of generations, then we may not get to the global minima. So now for each generation we run this. Inside the while loop we run one more while loop. And how do we do it? First we take j, again I index j. Now this j, we take the initial value as 1, and now we run a while loop for j. While j is less than equal to n var. N var is the number of variables, that is two variables, is x1 and x2. While j is less than equals to n var, we take f naught equal to f of x naught comma 1 and f of x naught comma 2. Okay, we do the function evaluation for the initial solution, that is x naught is c2 comma 2. We do the function evaluation. Now we substitute that new solution, that is y is equal to x naught, and we have to update this y value. Now y of j, that is y of first part, that is y of 1. Y of 1 will be what? The first component of the y array. That is, y will have two elements like y1, y2. Similarly, because x has two elements, 1 comma 2 elements, x naught. So y will also have two elements, and the first element will be updated based on the elements will be updated based on j. Now for initially j is 1. When j is 1, so it will be working on the first element of y matrix. And how do we use that? We get yj equal to x naught j plus r norm 1 mean comma 0, mean equal to 0, and sigma standard deviation equal to sigma. And y1, we are generating only one random value from the Gaussian distribution. So we got the y value, and now we do the function evaluation f1, that is after first iteration or the next iteration, we get f of y1 comma y2. So initially now we have got a new value of y1, and y2 will be what? It will be same as that x naught comma 2, because the first iteration we are not changing the y2 value. Y2 value will be changed when the j value is changed, that is j becomes equals to 2. So now we got the function value. Now if f1 is less than f0, we learned in the method that if f of y is less than f of x, so we run a if condition, that if f1 is less than f0, we get x naught. We replace y value as x naught, and we proceed to the next solution. That is the new next iteration, the x naught value will be replaced by y. So we see the points, how the point is varying after each iteration. System.sleep is kept as 0.3 to visualize the solution. Okay, let us keep as 0.2. So now I update j, and we also update I, that is I equal to I plus 1, j equals to j plus 1. So let us run this code. I think I'll change the color to get a better value. Okay, you see we have to keep purple only so that we can see. Yeah, you can see this purple value is varying for 1000 iterations. Okay, let us keep as 0.3. This algorithm is very fast, so that's why we have to keep the system.sleep equals to high. Yeah, you can see after 1000 iterations the Let us start with I equals to 1 and then run the while loop again. Yeah, it is very fast algorithm. So after 1000 iterations, we were getting the minima near the near the global minima. So print x naught towards 2.99 and 2.0 that we initially got with the multi-member ES. For two-member ES also, we are getting the same solution. And function value is like 2.6 into the minus 6. That is, it is better than the multi-member ES. So sometimes if we take the initial solution, but the thing is that this initial solution for the population is very important in case of this two-member ES. You have to select that carefully. If we take it too far, then it will have like more number of solutions. So let us try to keep somewhere around like minus 2 comma 2 and then we will see. Okay, now let us see what we got. Yeah, you can see in now we have taken the initial solution near minus 2 here. So we're getting the solution, the minima that is nearest to the initial population, that is you are getting the minima here is minus 2.8 and 3.13. So it is like that. So if we take the solution far away from the global minima, you will get near the local minima only. But if we use the multi-member ES, so that will always converge to the global minima every time. Okay. So this is the main difference between this two-member ES and multi-member ES. Okay. So if there are any doubts, you can ask me now, or else we'll proceed the particle swarm optimization.
Sir, the
Yeah.
coding will be the same basic, only the function gets varied here.
Yeah. The main theory is same. I told discuss in the class also, no? So the in multi-member ES, what we do generate when we take the initial population, we are taking around 20 or 30 solutions. So we're taking a huge
Okay.
number of population and we are proceeding to try to get the minima from each of this solution. But when you're taking two-member ES, what we do, we take only 1 point in the solution space. We take only 1 point and try to update the value of that point only. So if the thing is
Okay.
that in the two-member ES, if the initial population is far away from the global minima, it is somewhere near to a local minima, it will then even after a higher number of iterations, it will converge to the local minima only. So that is the difference
Okay.
between this multi-member ES and two-member ES.
Okay. Thank you.
Okay. Okay, so this was about ES algorithm. So it's a very good, powerful algorithm, but you have to use it carefully because based on the requirement of global minima or local minima. Now we'll see this code on this one, particle swarm optimization. This has a already defined function that is developed by in this package PSO. So we do this install of package as PSO, then we load the library PSO. And so what we do initially, okay, I will remove this. Okay, I will remove this workspace also. Okay. So do the question again the same question only, that is f equal to x1 plus x2, that same question that we did in ES algorithm. So we get the function, we generate x1 x2, we get z. Now for z we generate this contour plot. We can see the same contour plot only. I think we have generated number of levels as 200, so that's why we're getting two number higher the density of the contours. So now we have to get the function in PSO, again similar like genetic algorithm where it can take only one variable. So you have to convert this x1 x2 into an array. So similarly and this method is also a maximization kind of method. This is again like a maximization kind of method, and yeah. So what we do, we multiply the function by a negative sign. So we get the function, we get set dot seed equals to 1. This set dot seed is used, like suppose if you are repeating the solution for a higher number of times, it will preserve the solution. Which will get more advantageous is like based on the requirement sometimes, but in general ES is very fast. It will converge to solution very fast, but thing is that you have to write the code. And even PSO is a very fast algorithm, because in PSO you are doing this global search and local search faster. So PSO is better than genetic algorithm, and ES is depends on the requirement. So if we compare all the three, I think PSO is the best among all the three, followed by ES and GA. But the thing is that in case of GA, you have higher diversity, like higher, you can do a lot of changes in the code. Like you can change the mutation parameters, you can do crossover. Like in ES, you cannot do crossover. So if like your problem is very complex, in simple kind of functions, the thing is that ES or PSO is very good. But sometimes for some very complex problems, in that case, GA, in GA you can change all the parameters in like such a way so that you have higher control in your hand. That is, you can change a crossover, you can change mutation, you can keep elitism, everything. So there is higher, more power to you. But in case of PSO, you don't have much power in your hand. You have to give the parameters like mostly which are already defined, already fixed. Okay. So like in GA, what happens, like if suppose you don't want a global minima or global maxima, you want some local minima. So you can change the parameters in that way, it based on a requirement. Okay. So we put set dot seed equals to 1. So now we proceed. So this result function, we use this function PS optim. What this PS optim does, it's does the optimization using the PSO function. So the first parameter is CA NA comma 2, and you can put some initial value or you can also relieve it. So we'll keep it as NA, so that we don't want to put any initial value to the function. So and we put 2 so that we are taking two solutions, that is two values, two number of variables. Now we take f is the optimization function. The lower limit is -5, upper limit is 5. Now control, in control we put that is tolerance level of 1 e minus 8, that is 10 to the power minus 8, so that after reaching suppose even before yeah, after reaching a tolerance level of 10 to the minus 8, that is the difference between like next iteration and that iteration, if it is less than 10 to the minus 8, will stop the procedure. CP and CG, this is C1 and C2. It is the probable, CP is for the personal best, CG is for the group best. So we'll put this C1 and C2 values, that is C1 is kept as 0.5, C2 is 0.9. You can change these values based on a requirement. And then I'm putting hybrid equal to hybrid. What does the hybrid function does? The hybrid function, like if we want to combine this deepest descent method along with this PSO method to get more accurate solutions in a faster way, we can put hybrid equals to on. So we'll run this code, we'll get this residual function. This very fast. Again, let us put the points after the after we got a we put it as like red. Okay, I think we got somewhere here. Put function equals to this one only, right? Yeah, I think we're getting the minima somewhere here. Let us see if we what we run again. Yeah, we're getting the minima in this range. So if we change the function, suppose if we keep it as positive, Now what it happens? Yeah, now we are getting, yeah, so this was the mistake. So yeah, sorry, this was my mistake. In PSO also we need not multiply it by minus. It is by default a minimization kind of method. So if we put the first one, you can see, okay, we'll plot the contour. Now we'll do this. We got near the local global minima. Again we'll run. If we see what we get. For a second. Yeah, we're getting there only. Yeah, we're getting in the near the global minima only. Yeah, sometimes you might be getting near the local minima base if we put this personal base and CC parameters slightly different. Okay, so simple code, only one line code only here. You have to use this PS optim formula or this function. So this is one question that we'll try to solve, where this is function is given 10 plus x1 square minus 5 x1 into x2 plus 9 x2 square plus x2. So we put the function as this one. Okay, so we again use this result function is in PS optim. We take the initial value as 0. Before we gave the initial value as NA, here we keep the initial value as 0. We put, then we get the location parameter. Location is where? Location you can see. It is minus 0.45 minus 0.18. We're getting this value. So what is the function value at this location? So print function value is 9.901. Okay, so it is a simple method. You can just by writing the function, you can do the optimization only using one step only. So in PSO, you need not define any mutation and crossover here. Here the thing is that the local search and global search are done simultaneously. Now if CP and CG are not defined by you, in that case what happens, it takes this default value, that CP, it is given here. This is this PS optim function. You can go to help and have a look at it. Yeah, CP default is 0.5 plus log 2. This log 2 is around 0.3, so 0.5 plus log 2 is 0.8. Again, even for CG, the value is 0.5 plus log 2, this is 0.8. Both the values are kept as 0.8 and 0.8. If you change these values, you might get slightly different solutions, slightly varying from the initial solution. Okay, so yeah, so this was about particle optimization. Okay, any doubts you have? Yeah, if you have any doubts, you can ask me now, or else this is the end for today's session. Okay, then if there are no doubts, we will end the session. And so this Monday there will be no class. The next class will be on, I think, 7th, 9th October. Okay, so 9th October we'll have the next class. So
Sir, I have one doubt, sir,
yes,
regarding to PS work.
yeah.
Is there new solution is obtained using the position update need not be within the bounds of the decision variable, sir?
Like, yeah, it is like that only. The new solution is obtained, like if we take a initial solution, so the solution will be
Okay.
updated by doing this global search as well as the local search from the initial solution. So it will be doing all these things together. So
Within the bounds or not restriction?
yeah.
Okay, okay, sir.
Hmm. Okay, then if there are no other doubts, we'll end today's session. I think, yeah, that is all. Have a good weekend. Bye bye.